Shear.
In this lesson we're going to talk about web shear. First off, we need to find out what a web is. If you have an I-beam, here's the top flange, okay, and here's the web, and here's a bottom flange. So this part right there would be the web. So in our previous lessons we talked about trusses with zigzags. Here's one. Okay, let's say this is a fishing truss as opposed to a fishing pole. We have a 50-pound fish hanging from the end of it here. So at this point, this zigzag is in tension. It's having to hold this point up because the fish is trying to pull it down. Okay, let's say these are all 90-degree angles right there, right there. That's a 45, that's a 45, a 45, a 90, a 45, a 90. Okay, in other words, we have a bunch of 45-degree right triangles here. Let's say our truss from top to bottom is 1 foot high. Okay, so that means it's 1 foot from there to there. And with this dotted line, we just turn this 45-degree right triangle into two smaller 45-degree right triangles. So if that 1 foot there is equal to this 1 foot here, that's a leg, this is another leg of this 45-degree right triangle. So from here to here is 2 feet. Okay, so we have our truss here, our zigzag, pulling 50 times the square root of 2 pounds because the ratio of our sides of a 45-degree right triangle are 1 to 1 to the square root of 2. Then 50 times square root of 2 is 70.7. So that's in tension, which means it's pulling this point down and to the left. Well, this zigzag has to be in compression because its vertical component cancels out the vertical component of this tension member. This one's pulling down and to the left. This one is pushing up and to the left. Okay, the up from this one balances out the down from this one, but they're both moving, trying to hold this point to the left. They're forcing it to the left. As we can see, if this truss were a stack of paper, like so, and we didn't have our tension member here, or our compression member here, and this fish was hanging from here, it would pull it down like this. This would become further away from this. This would become closer to this because this tension member would let it get further away, and this compression member would allow it to get closer together. So, okay, we have 2 feet between here and there. Every 2 feet we have another pair of zigzags touching our top flange. Okay, remember the name of this lesson? It's web shear. We looked at the web of an I-beam at first, and we're going to look at how a web takes the place of the zigzags of a truss. So these zigzags, this zigzag here is in 70.7 pounds of tension. In other words, it's pulling this point down 50 pounds, it's pulling it to the left 50 pounds. This one's pushing this point up 50 pounds, pushing it to the left 50 pounds. The ups and the downs cancel out. So the net result is that at this point, this pair of zigzags is holding this top flange to the left 100 pounds. These zigzags are doing the same. We're assuming this is a weightless beam, and the only weight here we have is the fish. Of course, that's not the way it works in real life. All beams in real life do have weight, which means that these zigzags would become under greater loads as we go further and further this way. Okay, so we have 100 pounds pushing this top flange at that point, another 100 pounds pushing it to the left at this point, another 100 pounds pushing it to the left at this point. In other words, every 2 feet we have 100 pounds. So we can come up with a formula for web shear, because we can say that the horizontal shear force of 2 zigzags, or the horizontal components of these 2 zigzags, which is 100 pounds, equals the shear force of a 2-foot section of a web if we were to replace these zigzags with a web. So what is the horizontal shear force of the 2 zigzags? Well, it's this 50-pound weight of the fish gives you a 50-pound horizontal component, which is why this zigzag has a 50-pound horizontal component. Okay, and this one too. So 2 times the vertical shear, which is what this fish is causing. 2V, 2 times vertical shear, is the force here. It's equal to 2 times, well, here's the height of our beam. We call it 1 foot. We could call it H if we want. But whatever we call it, from here to here is twice as much. So if we call it H instead of 1 foot, well then it's 2H from here to here. So 2H, that distance, times T, the thickness of our web. Remember our web, let's see, here was an I-beam we looked at in a lesson or 2 ago. If we were to cut it right there, cut the web off from the top flange, cut the web off from the bottom flange, it would look like this. There's the top flange, there's the bottom flange, there's the web. Okay, so right along in here, that'd be the area where the web connects to the top flange, right underneath there. So this area of our web between here and there times the stress in that area will give us a force, which is equal to the force that these 2 zigzags are pulling on this point. That much force for every that distance. So getting back to our formula here, horizontal shear force of 2 zigzags, which is 2 times the vertical shear force, in this case 2 times the weight of our fish, plus the weight of our beam, which we're calling weightless in this example. Okay, the horizontal shear force of these 2 zigzags, 2V, equals the area of our web along here from one connection to the next, which is 2H times T, times the stress, the shear stress in our web. So we have 2V equals 2 times height times web thickness times the stress of the web. Well, we can divide each side of the equation by 2 and we get rid of them. We can divide each side of the equation by H times T. We end up with shear stress equals the vertical shear divided by the thickness of the web times the height of the beam. That's how we figure shear stress in a web. We determine that the web shear stress, the stress in the web of our I-beam, is equal to the vertical shear force divided by the height of the web or the beam, doesn't really matter which one, they're both about the same, times the thickness of the web. So here we have an I-beam. Let's say it's resting on a stand on this end and resting on a stand on this end. Let's say this I-beam has a weight equal to W. So the force here would be W over 2, 1/2 W. And the force on this end would also be W over 2. So the shear force at this point would be W over 2. But as we move along this way, our shear force is equal to the force pushing up here minus the force of the weight between here and wherever we're measuring our vertical shear force. So here, halfway across the beam, between one end and the other, the vertical shear force is going to be W over 2 minus W over 2, because the weight of this whole thing is W. The weight of half of it is W over 2. So at this halfway point, the vertical shear force is going to be W over 2 minus W over 2, which is 0. Just like in our stack of paper that we were lifting with 2 bridge supports. We have shear stress here on the ends, but no shear stress in the middle. Our I-beam right here is similar. No web shear in the center of it. But let's say we have another I-beam here, kind of like this one. Let's say this one is identical to this one. Same length, same weight. Let's say we tie a rope around this and we hang it from here on the end of it. So we have a load of W hanging off the end here. That's what this weighed. We called it W. It may be 100 pounds, maybe 1,000. We don't care. We're just going to call it W. Okay. Well, the vertical shear force at this point will be W. Okay. The vertical shear force halfway between here and the end. Let's say this is going into a wall or something like that, holding it in place, where the weight between here and the wall is the same as the weight of this one. Well, halfway between here and the end, our vertical shear force is going to be the W hanging from there plus 1/2 W, because between here and there the weight of this beam is 1/2 W. So it would be 1.5 W, which means the vertical shear, or the web shear, the vertical shear at this point would be 3 times what it was on the end of this beam sitting on 2 stands, which means the web shear stress would also be 3 times as much. You know, assuming we have the web with the same height and thickness all the way down. Okay, let's say we wanted to build our own beam out of angle iron, angle aluminum, angle fiberglass. We're not really talking about materials in this lesson. We're talking about determining the loads on certain segments. Okay, let's say here's a piece of angle iron, here's a piece of angle iron, and here's a flat sheet in between them. There's another piece of angle iron on the bottom, another one there. 4 pieces of angle iron and 1 flat sheet. And we're just going to drill holes through here and put bolts through it. Call them bolts, rivets, whatever. We'll talk about rivets in a future lesson. But right now, let's try to figure out how many rivets we would need in this. Let's say we're talking about the same configuration we talked about a while ago with this truss. Remember our 50-pound fish hanging from it? Our web shear was 100 pounds here. It's another 100 pounds here, another 100 pounds here. Every 2 feet along the top flange, we had 100 pounds of shear added to it, of shear force between our zigzags and our top flange. In this case, it would be between our web and our top flange. So if we have to withstand 100 pounds every 2 feet, and one rivet can handle, let's say, 50 pounds, well, we would need 2 rivets every 2 feet, or 1 rivet per foot. It doesn't sound like much, but then a 50-pound load isn't much either.